Hi everybody. That's the first session of the revision, and the first session will be reviewing capacitors. So let's just start the first example. The first example of capacitor. You have a capacitor where C is equal to 50 microfarad, and the charge accumulated through charging process was equal to 4 millicoulomb. The question is, what is the energy stored in C during this process? Okay, when you solve this problem, then you should know the formula used to calculate the energy stored in a capacitor. We learned that the energy is equal 1/2 CV squared. But the problem is we do not have the voltage. Instead, we have Q. So you got to find the relationship between Q and V. You know that Q is equal to CV. Accordingly, the voltage V is equal 1 over C times Q. So if you replace volt in this equation of the energy, so the energy will be equal to 1/2 C and V square, and V is equal Q over C. So it will be equal to 1/2 C Q square over C square. So it will be equal Q square over 2C. And you just start to substitute. Q is equal 4 millicoulomb divided by, and that's, by the way, it's going to be square, divided by 2 times C, and C is equal 50 micro. And just simplify the equation and you will find the energy in joule. So that's it. So the aim of this example, yes, you know the formula for the energy, but if you don't have variable, you got to find the relationship between this variable and the variable given in the problem. Okay, let's move the second example. In this example, it's giving that a capacitor and C is equal to 0.5 microfarad, and the voltage across the capacitor is equal to 12.5, 1 minus E minus 200T. It's required to find the current in the capacitor at time equals 0. B. Power delivered to the capacitor at T is equal 8.05 millisecond. C. The energy stored in the capacitor at T 8.05 millisecond. Okay. So the first part, to find the current at T equals 0, you should first find the current at any time T. The relationship between the current and the voltage across the capacitor is C dV by dt. So the current is equal to, the capacitor is equal 0.5 microfarad 10 minus second times dV by dt. So we have to differentiate the equation of the voltage. So you have 12.5 is a constant. The derivative of 1 is equal 0 minus the derivative of the exponential part is equal to E minus 200T times minus 200. So simplify the equation, you will find that's equal to 0.1 E minus 200T. That will be the current at any time. Now we can substitute by T equals 0 in the above equation. E power 0 is equal 1. 1 times 0.1 is equal 0.1 ampere. So you can say it's equal to 100 milliampere, and that will be your answer for part A. Part B. find the power at t equal 8.05. How can you find the power? Well, the power is given by voltage times current. This formula is applicable for resistor, inductor, capacitor. It's a general one. All right. So, and you want to find the power at a specific time. So, the power at time equal 8.05 millisecond will be equal the voltage at the time 8.05 times the current at 8.05. So I'm supposed to get this one. So first, I want to find the voltage at 8.05 millisecond. I have the equation of the voltage here in the top. So I'll say it's equal 12.5 1 minus E minus 200 and the time 8.05 times 10 minus 3. Do it in the calculator and you may check it. So it's equal to 10 voltage. So I got the voltage at this one. And the time and the current, I have the current at time t. Substitute by the 8.05 at the equation of the 0.1 E minus 200t and t is equal to 805 10 minus 3. Doing in the calculator will give us 0.02 ampere, which is equal to 200 milliampere. So that's the current at this specific time. So the power at time equal 8.05 millisecond, the product 10 times 200. Oh, I'm sorry, that's 0.02. It's not 0.200. It's going to be 20 milliampere. Sorry for that, 20 milliampere. So multiplied by 20. So you got 200 milliwatt because I used milliampere here. So that was part B. Part C, the energy stored at time t equal 8.05. So how you find the energy? I know that the energy it's equal 1/2 CV square. And you can do that. But I have another formula to use also. But why I don't use this one? Is it wrong? No, it's right. But when I square the VC, I want to do it in a different way, not square the function. So I will say, the other thing, that the energy is equal to the integration of power with respect to time. So that will make it, maybe simple. So the integration of the power, and power is equal voltage times current. And so the energy equal to the integration of the voltage. So I multiply the voltage, which is 12.5 1 minus E minus 200t times the current. The current is equal to I have here the current, yes, with the equation 0.1 E minus 200t. So I have the two equation. So I multiply both equation and I integrate and I substitute from 0 to t first to get the expression for the energy as a function of time. Then I will do substitute by t is equal 8.05 and I get the result. So that was the idea behind solving in energy. Can we do the other one? Yes, you can do. If another solution that's using the formula, it's not wrong. It depends, which one you prefer. It's equal 1/2 CV square. So all what you're supposed to do is say 1/2 and the C is equal to 0.5 microfarad 10 minus 6 times V square V square, that's V is equal to 12.5. So you have 12.5, 1 minus E minus 200T, and that would be square. So you can do, square this function, multiply it. You don't have to do any integration or anything like that. And once you get the expression, substituting the n by t is equal 0.05. So that would be all. It's not a big deal. It's just involved a little bit in math. Okay. Let's now go to another example. Well, in this example, I'm going to explain RC circuit. Before, I solve the example, I just like to remind you by something, that the differential equation, general differential equation for RC circuit is tau dVc by dt plus Vc is equal to Vs, where tau is the time constant, RC. And the solution of this equation is the voltage across the capacitor at any time is equal to the initial voltage was stored in the capacitor before start charging process times E power minus T over tau plus Vs source that you have used to charge the capacitor 1 minus E minus T over tau. So that's the general equation when you are charging. When you are discharging the capacitor, the differential equation will be different. So let's just say this is for charging process. For this charging process, the equation will be tau dVc by dt plus Vc is equal 0. You don't have source here. And the solution will be Vc of t is equal V E minus T tau, and that was charged. That one was charged before. And if you want to sketch both solution, when you are charging, start from initial condition till you want to reach Vs, it will be charging like that. If you want this charge, that's Vc. And let's say that you are here and you want this charge, so it will go down like that till it goes 0. So that's charge, that's the charge. Tau is equal RC. Okay, now just let's go and solve the example. We have a switch, capacitor. The capacitor is equal 1/4 microfarad, and the switch was at position 1 in the beginning. We have resistance 20K, 60K, power supply 40 voltage. We have another position 2, 8 kilo ohm, 160 kilo ohm, 40 kilo ohm, power supply 75 voltage. So the switch was in position 1 for a long time. Then at t equals 0, S become in position 2. Required, find the voltage output Just look at, I will call it VC, not to confuse with the initial condition. We want to find the voltage across the capacitor at any time t for t greater than 0. B, we want to find the current in the capacitor at any time t for t greater than 0. C, the voltage across 160 kilo ohm at any time t for t greater than 0. This one. Okay. So let's start solving the question. First, the switch was in position 1 for a long time. It means it was like at steady state. So what is supposed to do? You sketch the circuit at steady state when the switch was as S1, position 1. So you have a capacitor, and that's position 1, and you got a resistance 20 kilo ohm, 60 kilo ohm, power supply, voltage 40 volt. At steady state, the capacitor behaves as open circuit, so you just open circuit. Then you try to find the voltage across the capacitor or in this open circuit at steady state. Well, it's very simple. The voltage at these 2 points is the same voltage across 60 ohm. So I'm going to use voltage divider rule. The voltage across 60 kilo ohm is equal to the total voltage 40 times the resistance 60 kilo ohm divided by the total 60 plus 20. It will be 40 times 60 over 80. It will give 30 voltage. So now I can say that the voltage across the capacitor for t before 0, it means before the switch goes to, just before it was 30 voltage. And we know that the capacitor cannot change the voltage instantaneously. It got to take time. So just after switching exactly, you'll find that the voltage, it's still the same, has to be the same. That's the main rule for the capacitor. Well done with part A. So you can say that the voltage at time equals 0 is equal 30 volts. Now go for part. Oh, we didn't do even part A. We just did half it. We'll prepare it. Because the question is find the voltage for t greater than 0. It means the switch is going in this direction. So let's go ahead and take this part of the circuit. Oh. That's wrong. I have to take another one. Oh man. Okay, that's the right one. I'm sorry for that. So that's, the part when the position of the switch at position 2. So I will just sketch the circuit. Oh, we have it here. So just you will connect S to 2. So it will be like that. 8 kilo ohm, 40 kilo ohm, 160 kilo ohm, and power supply 75 voltage, and you have the capacitor. Since you are going to calculate the voltage across the capacitor at any time t, you cannot replace the capacitor by open circuit. Question: when you replace capacitor by open circuit, you replace capacitor or you represent capacitor as open circuit when you are required to find the value of the voltage across the capacitor at steady state and DC condition. But at any time t, you got to get it. Okay. How to solve this one? Well, we know how to find the equation of the capacitor, as I explained here, by using the differential equation. This differential equation, and this is the solution. But this can only be applied if you have this circuit. RC. So the equation we just wrote here, differential equation, or the solution of the differential equation, it's only applicable if you have a simple circuit like that. Voltage source, resistor, capacitor, and tau is equal RC. In our circuit here, it's different, it's not the same. So you need to find the equivalent Thevenin. So the first thing we'll do, we'll find the equivalent resistance. How you find the equivalent resistance? But before we start, Thevenin, it means that you have a circuit and you got load. You're going to apply it to the output terminal. In this case, this is your load, the capacitor. So we have to look at the circuit from this side. I will sketch it in a way to find the resistance. So you have 8 kilo ohm, 40 kilo ohm, and to find the resistance, you make short circuit on the supply, on the voltage. Somebody may ask, what about if this was a current source? Of the current source, make it open circuit. Voltage source, make it short circuit. Since voltage source, we make it short circuit. And that's 160 kilo. And that's the output terminal where you put the capacitor. Remove the capacitor now. And look from this side and try to find the equivalent resistance, which we call it R Thevenin. The equivalent resistance, if you look at this side, if you say there is current going in this direction, so one part will go in this direction, another one, so the current will be divided at this junction. So since the current will be divided at this junction, so 40 kilo ohm and 160 kilo ohm, they are connected in parallel. So the R Thevenin will be 40 in parallel with 160 kilo ohm in series with 8 kilo ohm. So that will be 40 times 160 divided by the sum. That's the parallel combination of 40 and 160. And then you add it to 8. When you do that, you'll find it's equal to 40 kilo ohm. So now we know the resistance, the equivalent resistance of the whole circuit. Second step, you want to find the equivalent Thevenin voltage. So you sketch the circuit again. But this time, don't make short circuit on the voltage supply. That was 75 voltage. And find the voltage at the terminal AB here. What's the terminal AB? The terminal AB, that's where you are going to attach the capacitor or connect the capacitor. So what is the voltage here? Since it's open circuit, no current going through in 8 kilo ohm. So the voltage at AB, it is the same as the voltage across 160 kilo ohm. So you may sketch your circuit simply like that. (160 kilo ohm). So what's the voltage across 160 kilo ohm? You can find it using a voltage divider rule. So the voltage across this one is the same as VEB. So you will say that voltage across AB is equal the total voltage 75 time the resistance 160 kilo ohm divided by the total 160 plus 40. So the result will be, okay, 60 voltage. So now you can sketch the equivalent circuit. You have 60 volt, you have R equivalent, which 40 kilo ohm, and then you connect your capacitor, and the value of the capacitor 1/4 microfarad. And now the circuit is very similar to the circuit we drove the equation and the solution. Let me summarize the information here. R is equal to 40 kilo ohm and C is equal 1/4 microfarad. So the time constant tau is equal R times C is equal 40 10 power 3 times C 1/4 10 minus 6. So the tau will be equal 1/100 second. So that's the tau. The voltage is equal 60. So write Vs is equal 60. So if you like to write the differential equation, tau dVc by dt plus Vc is equal Vs. Everything is given now. Tau is equal 1/100, 0.01, and dVc by dt plus Vc is equal Vs, which is equal 60. The solution is equal to Vc is equal V naught E minus T over tau plus Vs 1 minus T over tau. What's VO? The initial condition, and we calculate it here. It's equal to 30. So that will be 30. Just make space here. 30. E minus T tau. Tau is equal 1/100. 1 over tau is equal 100. So minus 100T plus Vs. Vs is equal 60. 1 minus E minus 100T. So that will be the equation of the voltage at any time. Of course, it depends on the time. Okay. Now, I mean, we're done with part A. Let's go back. EC of T. Now they want to find the current in the capacitor. How you find the current? Well, we know that the current in the capacitor is equal C dV by dt. So all what you're supposed to do, just multiply C, which is equal 1/4 microfarad, times the derivative of this one. The derivative here 30 times E minus 100T times minus 100 plus 60. Derivative 1 is equal 0, and the other one be E minus 100T times minus 100. And simplify this expression, you found IC, the current in the capacitor. Okay, what else we're supposed to do here? Well, just let me give you the answer so can you check if you work at home. I did it is equal 75 times 10 minus 5 E minus 100T. And by the way, if you want to simplify VC more, you can't work ahead. Just so when you have in the exam, some equation, so you can tell us right or wrong. Let me show you what I mean. 30 E minus 100T, and then plus 60 minus 60 E minus 100T equal. So you have 60 as a constant here, and then 30 and minus 60 be minus 30 E minus 100T. That will be VC. That's another way, because in the exam you're going to have multiple choice, so maybe you'll not find it look like that. Maybe it will look like that. So you got to simplify it to get it like this. Okay. All right. So now we got VC, we got IC. Let's find what else. They want to find the value of the voltage across 160 kilo. Okay, that's very interesting, because usually in the capacitor problem, the request to find only the voltage across the capacitor. No, now I mean they want to find the voltage across the 160 kilo ohm. So what should you do? Just use Kirchhoff. I will sketch it again here, the circuit. 40 kilo, 75, 160 kilo, 8 kilo, and VC. Okay, and the current IC going in this direction, so it will be also coming here, passing here. So you want to find the voltage here. So I will assume the polarity here is positive, here is negative. Let me make it look simpler. Positive, negative, I say this is the voltage across 160 kilo ohm. And that's the voltage if the current going in this direction, so that will be a positive and negative. So let me do it in the same way. And you got a voltage here, positive and negative. That's the voltage across 8 kilo ohm. And here you got capacitor, and the voltage, the positive in the top, here in the bottom, that is VC. Apply Kirchhoff voltage law. Kirchhoff voltage law will say that VC and the positive connected to negative will be plus V8, positive connected to positive will be minus V160 equals 0. So the voltage across 160 is equal to VC plus V8. VC, we got it. You tell me where this is VC. 60 minus, let us write here, VC is equal 60 minus 30 E minus 100, I believe. Yes, 100 T. What about V8? V8 is equal to the current through the 8 kilo ohm times the resistance 8. So you have 8 kilo ohm times the current, and the current the same IC, because I mean IC is going in the same direction. IC, I have it 75 times 10 minus 5 E minus 100T. Okay, so you multiply this one, so you get like you can check, you know, if I did the right calculation. E minus 100T, so that's V8. So you got V8, and and that's the equation. So then substitute voltage across 160 is equal to VC, which is equal 60 minus 30 E minus 100T plus 6 E minus 100T. It will be equal to 60 and minus 24 E minus 100T, and that will be the voltage across 160. I hope that this example, I mean, made everything clear for the capacitor charging and this charging. Okay, thank you for your paying attention, and the next video will be on the inductor. See you soon.